Introduction. Goldschmidt proposed atoms could be considered as packing in solids as hard spheres. This reduces the problem of examining the packing of like atoms to that of examining the most efficient packing of any spherical object. Example: have you noticed how oranges are most effectively packed in displays at your local shop? Objectives. At the end of this lesson, you'll be able to explain close packing of particles, describe different types of voids and close-packed structures, calculate the packing efficiency of different types of cubic unit cells, 7 primitive unit cells. There are 7 types of primitive unit cells. Their characteristics, along with the centered unit cells they can form, have been listed in the table. Unit cells of 14 types of Bravais lattices. The Bravais lattice are the distinct lattice types which, when repeated, can fill the whole space. In 2 dimensions, there are 5 distinct Bravais lattices, while in 3 dimensions, there are 14. These 14 lattices are further classified as number of atoms in a unit cell. Any crystal lattice is made up of a very large number of unit cells, and every lattice point is occupied by one constituent particle, atom, molecule or ion. In a simple unit cell, each corner is shared between 8 unit cells. Each cubic unit cell has 8 atoms on its corner. The total number of atoms in each unit cell is 8 into 1 upon 8, which is equal to 1 atom. Primitive cubic unit cell has been depicted in 3 different ways. Number of atoms in a body-centered cubic unit cell. A body-centered cubic BCC unit cell has an atom at each of its corners and also 1 atom at its body center. Thus, in a body-centered cubic BCC unit cell, 8 corners into 1 upon 8 per corner atom is equal to 8 into 1 upon 8, which is equal to 1 atom. 1 body center atom is equal to 1 into 1 equals 1 atom. Therefore, total number of atoms per unit cell is equal to 2 atoms. Number of atoms in a face-centered cubic unit cell. A face-centered cubic FCC unit cell contains atoms at all the corners and at the center of all the faces of the cube. Thus, in a face-centered cubic FCC unit cell, 8 corners atoms into 1 upon 8 atom per unit cell equals 8 into 1 upon 8, which is equal to 1 atom. 6 face-centered atoms into 1 upon 2 atom per unit cell, which is equal to 6 into 1 upon 2, which equals 3 atoms. Therefore, total number of atoms per unit cell is equal to 4 atoms. Close packing in solids. In solids, the constituent particles are close-packed, identical hard spheres, and build up the 3-dimensional structure in 3 steps. 1. Close packing in 1 dimension. In this arrangement, each sphere is in contact with 2 of its neighbors. The number of nearest neighbors of particle is called its coordination number. Its coordination number is 2. 2. Close packing in 2 dimensions. A. Square close packing. In this arrangement, each sphere is in contact with 4 of its neighbors and formed square. Its coordination number is 2. B. Hexagonal close packing. In this arrangement, each sphere is in contact with 4 of its neighbors and formed a 2-dimensional hexagonal structure, and its coordination number is 2. Close packing in 3 dimension. Close packing in 3 dimension can be obtained by stacking 2-dimensional layers one above the other. These are of two types: three-dimensional close packing from two-dimensional square close-packed layers. In this arrangement, the spheres of both the layers are perfectly aligned horizontally as well as vertically. The lattice thus generated is the simple cubic lattice, and its unit cell is the primitive cubic unit cell. Three-dimensional close packing from the two-dimensional hexagonal close-packed layers. These can be generated by placing layers one over the other. A. Placing second layer over the first layer. All the triangular voids of the first layer are covered by the spheres of the second layer. A sphere of the second layer is above the void of the first layer, or vice versa, are called tetrahedral voids. Such voids are surrounded by 6 spheres and are called octahedral voids. Placing third layer over the second layer. 1. Covering tetrahedral voids. In this case, the spheres of the third layer are exactly aligned with those of the first layer. Thus, the pattern of spheres is repeated in alternate layers. This structure is called a hexagonal close-packed HCP structure. Example: zinc. 2. Covering octahedral voids. The spheres of the third layer are not aligned with those of either the first or the second layer. This pattern of layers is called cubic close-packed CCP or face-centered cubic FCC structure. This arrangement is called C-type. Example: copper and silver. Formula of a compound and number of voids filled. While number of octahedral voids present in a lattice is equal to the number of closed-packed particles, the number of tetrahedral voids generated is twice this number. Locating tetrahedral and octahedral voids. Locating tetrahedral voids. Each small cube has 4 atoms. When joined to each other, they make a regular tetrahedron. Thus, there is one tetrahedral void in each small cube and 8 tetrahedral voids in total. Each of the 8 small cubes has one void in one unit cell of CCP structure. We know that CCP structure has 4 atoms per unit cell. Thus, the number of tetrahedral voids is twice the number of atoms. Locating octahedral voids. There is one octahedral void at the center of each of the 12 edges. It is surrounded by 6 atoms, 3 belonging to the same unit cell and 3 belonging to 2 adjacent unit cells. Since each edge of the cube is shared between 4 adjacent unit cells, so is the octahedral void located on it. Only 1/4 of each void belongs to a particular unit cell. Packing efficiency. Packing efficiency is the total space filled by the particles. Packing efficiency in simple cubic lattice. The atoms in a simple cubic lattice are located only on the corners of the cube. The particles touch each other along the edge. Thus, the edge length or side of the cube A and the radius of each particle R are related as A is equal to 2R. The volume of the cubic unit cell is equal to A cube, which is equal to 2R cube, which equals 8R cube. Since a simple cubic unit cell contains only one atom, the volume of the occupied space is equal to 4/3 pi r cube. Therefore, packing efficiency is equal to volume of one atom upon volume of cubic unit cell 100% is equal to 4/3 pi r cube upon 8r cube into 100 is equal to pi upon 6 into 100, which equals 52.36%, which is equal to 52.4%. Thus, we can say that CCP and HCP structures have maximum packing efficiency. Efficiency of packing in body-centered cubic structures. From figure it is clear that the atom at the center will be in touch with the other two atoms diagonally arranged. In triangle EFD, B square is equal to A square plus A square, which is equal to 2A square. B is equal to square root 2A. Now in triangle AFD, C square is equal to A square plus B square, which equals A square plus 2A square, which equals 3A square. C is equal to square root 3A. The length of the body diagonal C is equal to 4R, where R is the radius of the sphere atom, as all the three spheres along the diagonal touch each other. Therefore, square root 3A is equal to 4R. A is equal to 4R upon square root 3. Also, we can write R is equal to square root 3 upon 4A. In this type of structure, total number of atoms is 2 and their volume is 2 into 4 upon 3 pi r cube. Volume of the cube, A cube, will be equal to 4 upon square root 3 r cube, or A cube, which equals 4 upon square root 3 r cube. Therefore, packing efficiency is equal to volume occupied by two spheres in the cell into 100 upon total volume of the unit cell, which is equal to 2 into 4 upon 3 pi r cube into 100 upon 4 upon square root 3 r cube, which is equal to 8 upon 3 pi r cube into 100 upon 64 upon 3 into square root 3 r cube, which is equal to 68%. Packing efficiency in HCP and CCP structures. Both types of close packing, HCP and CCP, are equally efficient. Let us calculate the efficiency of packing in CCP structure. In figure, suppose the unit cell edge length BA and face diagonal AC is equal to B. In triangle ABC, AC square is equal to AB square plus BC square, or B square, which is equal to A square plus A square, or B square, which is equal to 2A square, or B is equal to square root 2A. If R is the radius of the sphere, we find B is equal to 4R, which equals square root 2A, or A is equal to 4R upon square root 2, which is equal to 2 into square root 2R. We know that each unit cell in CCP structure has effectively 4 spheres. Total number of 4 spheres is equal to 4 into 4 upon 3 into P r cube, and volume of the cube is A cube, or 2 square root 2 r cube. Therefore, packing efficiency is equal to volume occupied by 4 spheres in the cell into 100 upon total volume of the unit cell %, which is equal to 2 into 4 upon 3 pi r cube into 100 upon 2 upon square root 2 r cube, which is equal to 74%. Did you know radii of octahedral and tetrahedral holes? The size of an octahedral hole or a tetrahedral hole in a close-packed arrangement will depend on the size of the ion which is close-packed. The following table shows the change in atomic radii with coordination number. For comparison of atomic radii, all are corrected using the above factors to a coordination number of 12, even if their typical crystal structure has a lower coordination number. These radii are sometimes referred to as Goldsmith radii. Summary. Let us summarize what we have learnt. 14 different types of lattices are possible, which are called Bravais lattices. Each lattice can be generated by repeating its small characteristic portion called unit cell. Close packing of particles result in two highly efficient lattices, hexagonal closed-packed HCP, and cubic closed-packed CCP. The remaining space is present in the form of two types of voids, octahedral voids and tetrahedral voids.